Welcome everyone to Passive House Accelerator's 15th Global Passive House Happy Hour of our second year and episode number 67. Thanks for joining us. I'm Prudence Herrera, senior member of the Carbon Neutral Design Group at BR+A Consulting Engineers and lead their Passive House team. And every Wednesday night, your host right here. No matter why you're here and how you found us, you're in the right place. We welcome everyone. And if you are just joining and weren't here for the last few minutes, we have been talking weather and weather extremes. And I'm definitely in a part of North America where the temperatures are bad, much too high, really dangerous. I've been hearing about 106 degrees Fahrenheit in Seattle, 116 in Portland. My friends up in Canada are reporting they've had some 45 degrees Celsius days with 39 indoors. So no matter whether we are using the PHI approach to Passive House or the FIAS approach, one thing seems extremely clear, that overheating is real, and it seems critically important that we as a community try to gather as much data and make concerted efforts to get monitored plug load and lighting data that informs how we account for internal gains in our super insulated and airtight buildings that we're designing, so that we're aware of when we could potentially have overheating issues and are addressing those while we're creating the buildings. Data has no ego and definitely can be a strong uniting force for evolution and continual improvement. And so I would like to open this show by inviting you to unmute yourselves and join me in a toast to data. Here's to data.
Here's to data.
Here's to data.
Let's hear it for data.
And Spock.
All right. That's right. So we've got a great show for you. James Ortega, the certification manager of FIAS, is here with us, and we'll be sharing some juicy data on a senior living passive house project. But first, over to Zach.
Yeah, absolutely. So we have a cool video to share with you from Nikun Contracting. This is a time lapse of a 3-story passive house construction project, mass timber. So I'll share it now. Very cool. I love this video. It's a great project and also great interpretive labeling, I thought. So yeah.
Yeah, we definitely want the link to that video though. That was a way cool video.
Yeah, didn't they do a great job?
Yeah, they really did. Actually, I was just talking to Ottawa Community Housing. They're doing like a city block of FIAS plus passive house in Ottawa, and I'm trying like hell to convince them to do mass timber. They're already asking for an exception to do wood, and I'm like, 9-story wood, like we got to do mass timber.
Yeah,
I keep
yeah.
telling them how much shorter the construction time is, but like to be able to show them this,
Yeah, yeah. Yeah, that's awesome.
that would be great.
Definitely. If you have just arrived, we're in small breakout rooms right now. So this is the fashionably late foyer of the happy hour as we wait for people to go through the to do their small groups. So I'm Zach. I'm with Passive House Accelerator. I'm in Seattle, and glad you're here. If you want to say hello, feel free to do so. Thanks for coming. Right, I think people are back. I had many requests for the link to that cool video we just saw, so I'm just included it in chat there, the YouTube video. And I'm going to make some quick announcements, and then we'll get into the program here. So every week on the Passive House Accelerator, we do a weekend preview. So here's the Passive House Accelerator website. You can go to explore articles, and there's the Passive House Weekend Preview, which talks about what's coming up. And we have a great podcast episode with our very own Sean St. Amor. Matthew Cutler-Welsh has a really fun conversation with Sean about Sean's background and journey to Passive House, his family business and construction, and all sorts of great stuff. So please check that out. Tomorrow we have a component spotlight with Zola Windows. I'll talk a little bit about that at the end of the program, but please join us tomorrow at 10 a.m. Pacific, 1 p.m. Eastern to learn about window solutions for landmarked buildings. And we also have the new Gravity Accelerated Edition where we're working with Green Building United to put this conference on in July, on July 21st and July 22nd. So you can register now and save the date. Of course, we've got the International Passive House Conference, FIASCon, the Tower Retrofit Symposium. So you can get all the details about that, all these socials, including BS Fridays. This is co-hosted by Mark Willey, and this episode will feature Doug Farr of Farr Associates, he's fantastic, and then all sorts of educational programming. So please check it out. And with that, Prudence, please
All right.
take it away.
Thank you, Zach. So it's my pleasure to introduce James Ortega. He is the project certification manager for FIAS, and he's a smart cookie. After graduating magna cum laude from the Illinois Institute of Technology in Chicago with a Bachelor of Architecture in 2015, he started his career at FIAS. So he's been there since he started working. And he started out as an assistant to the project certification manager, Lisa White, became a CPHC, and then through his hard work and smarts, he has made his way up to being the certification manager, and he doesn't miss a thing. So in 2018, along the way, while he was working at FIAS, he became a licensed architect, studied for his exams, and then in 2019, he stepped up into the role of project certification manager. So he reviews all of the projects that come in for pre-cert and certification. He also does feasibility studies, consulting services also on dynamic energy modeling using WUFI Plus and Therm. And in addition to his role at FIAS, he's also a member of the technical committee. And that technical committee essentially shapes the FIAS Plus standards that are currently in effect and being developed for the next 3-year cycle. He also gives technical input to all of the FIAS programs like the Verified Window Performance Data Program and the Panel System Program, the training curriculum, et cetera. He's got his hands on pretty much everything. So James, we're thrilled to have you here, and I'm excited for you to share all of your good data with us.
Excited to be here. Thanks for the intro, Prudence. Let me share my screen, get this in this get this presentation started. Let me open up the chat because sometimes there are questions that come up in the chat. I will do my best to address stuff as we go, but I got a lot to cover and it's kind of an interesting subject. So let's just dive in. So I'm going to give you a brief overview of what this building is exactly, kind of the two main dwelling units that we have really granular data on. That granular data is mostly related to indoor air quality and plug loads and lighting. And then we're also going to take a look at the domestic hot water and then do some what I call energy sleuthing for the heating, cooling, and ventilation, because it's kind of a hodgepodge of information that I got for this particular building. So this is the building. It is certified project number 1366 on FIAS's website. It's in Guilford, New Hampshire. It is a senior living facility, so it's all one-bedroom apartments, 26 of them. It's only 2 stories, and we've got central laundry and then some semi-decentralized heating, ventilation, and air conditioning systems along with the hot water, which made this kind of tricky to pull stuff out of. Okay, so mechanical systems. We have 4 outdoor condensers serving all of the units in this building, and we have monitored data on 2 of them. So I know about what half of this building does. The electric tank water heaters, again, there are 7 of these that serve a variety of the units, and we have monitored data on 2 of them. There are 15 ERVs that serve these 26 units in addition to the common spaces, and 5 are monitored. So I'm going to give you my best partial picture of these bigger systems that I can, and then we'll work our way through the other stuff. So this is the general floor plate of the building. It's kind of an H shape, and basically the 2 units we have are unit 104 in the top right corner, and in the middle central section we have unit 107. Again, they're both 1 bedrooms. Unit 104 is obviously much more exposed. This one's got 3 of the walls exposed. And in addition, this does not have a second level unit directly above us. So it's actually roofed directly above that unit 104 as well. So I have data on 3 ERVs, and I have combined data on these 3 ERVs. One of them definitely serves unit 104. I'm not sure what the other 2 ERVs serve because the clamp installed was clamped after the panel, not directly at it. So I got a little bit more data than I know what to do with, because I don't necessarily know which unit is getting that airflow and served by that ventilation unit. I've got heat pump data on the water heater, or sorry, not heat pump, electric water heating data on units 103, 104, and 203, because that's what the first water heater serves. It serves 3 individual units. And the heat pumps themselves serve basically the whole east portion of the building is heat pump 1, and heat pump 2 serves the central portion of the building. And I'll have a diagram that'll kind of explain that a little bit later. Unit 107 is kind of similar. It's on a different heat pump section, and a different water heater serves it along with a couple other units, as well as a different set of ERVs on that same clamped data. Unit 104, the individual data we do have that's really good is we know for sure what the refrigerator uses. We know how often they cook. We got broken out data for the lights and the miscellaneous electric loads. And then I've got data on this, on one of the Renew Air EV90Ps, which is the ERV for this unit. The interesting part of this ERV location was it's not actually in the unit. It's in a mechanical closet kind of adjacent on the floor above it, which made, I think, the ductwork a little trickier to get to this unit, but kind of interesting anecdote. And then the project did use Mitsubishi heat pumps for the space conditioning and Rheem tanked water heaters for the domestic hot water. And again, the water heater was not in unit 104. It's actually in the unit right next door in unit 103, but that water heater serves both units. So fun data start. This is the really granular stuff I have in terms of individual plug loads and lighting energy. So kind of the interesting stuff, this is a senior living facility. So you'll see here kind of at the beginning of the year, there's these blue data here, which is related to a nurse's space. there's kind of like a station inside the room that's set up for nurses' equipment. And it was pretty interesting that I don't know if this person was suffering from an illness or something, and then they recovered from it. But that data really only shows up for the first 4 months, and then it drops off like that wasn't used anymore, which is kind of interesting. The range usage is kind of all over the place a little bit. Sometimes they cook more, sometimes less. Refrigerator actually was using less energy than we thought it was going to, and I'll show you in a second what the modeled uses was compared to this actual monitored data, which is always the question, right? Like how are we doing in terms of our predicted versus our actual stuff? So we did not do too poorly on this particular unit. So starting up at the top, the green line, and for these diagrams, just remember that if it's a dashed line, that means that was something we were assuming and predicting during the pre-certification and final certification process. So that is energy modeling data. It's not real data. The solid lines are the actual data. So for the lighting and miscellaneous electric loads, we were pretty close. I mean, on the average for the whole year, it varies a little bit month to month, while we were looking at, basically average monthly values for the lighting and miscellaneous electric loads. So not too bad in the green bar. And then the lower two are showing out the broken out refrigerator and the range. And they cooked a little bit more than we expected them to. And the refrigerator used a little bit less energy than we thought it was going to. So even less than the rated value of that refrigerator. So they kind of netted each other out basically. And in total, we're really, really close for a yearly average of how much energy was used in this particular unit by itself. So not incredibly exciting, because nothing is really that far off. And we're about 99% in terms of predicting what they would use on an annual average for their lighting, miscellaneous electric loads, and the range and refrigerator, which is kind of cool. Let's see. I see a message came in. What is the actual occupancy versus modeled? This is something I am not privy to. I would probably assume that these units have just one person living in them as their single bedroom senior living facilities. But according to FIUS's protocol, we usually assume one occupant plus a bedroom, basically. So number of bedrooms plus one is what we'd normally assume. So I think for this particular building, we would have assumed 2 occupants in this space, but I don't really know what the distribution is. Sometimes you can have 2 people living in the same space, but I am not sure. Unit 107, all of the same stuff. They have the same refrigerator, same range, same ERV. All this stuff is exactly the same, and we can take a look at the differences here. So in this particular case, they did cook a lot more, and you'll see that in the next slide, but this is kind of the same distribution. We had granular data on kitchen outlets, bedroom outlets, and the range in the refrigerator, as well as that smoking nurse's room. So this data, we actually over-predicted by a bit on the lighting and miscellaneous electric loads. They used quite a bit less than we expected them to, but you can see by the red line that they cooked a lot at the tail end of 2018, all the way through for almost a whole year through October. So this particular person or whoever is living here cooked a lot more than we thought they were going to, and kind of tailed off in the mid 2020. So that's just kind of anecdotally interesting. And we weren't as close as we were on the first unit in terms of our total predicted versus what was actually monitored. But it's pretty close. And, this is nothing to sneeze at. I think we're still within like 10% or so of what they actually used. So it's just interesting to kind of see like a very high level look into somebody's life that I don't know anything about them, but I know when they cooked, which is kind of a weird thing to think about. So next slide I've got to look at here is talking about indoor air quality. So this is always a interesting topic, and very important, near and dear to me, because it's such a, we don't really know what's happening in these buildings until we monitor it. So in this case, we have data on relative humidity, carbon dioxide, and volatile organic compounds. So from the relative humidity point of view, this is the monitored data in the kitchen of both units, 104 and 107. And you can see that in winter, it's getting really dry for the average day, basically getting below 20% relative humidity for at least a couple of weeks at a time, which is really, really low. And this could be a combination of things that could lead to this. These ERVs, these EV90Ps, have actually very decent latent moisture recovery for winter. Like it's supposed to be like 70%. So the two things that could be happening here are that either the occupants in this space are lower than we expected them to be, right? So there's lower moisture gains from additional people. The ventilation rates could be a little bit high in addition to that, which would mean that the space has more air changes. And the last part, which I will allude to the domestic hot water stuff, is these occupants used a lot less hot water than we were expecting them to. So maybe maybe they're not showering as often or as long of showers or something along those lines, but any number of these could kind of lead into this relative humidity number. Next graphic here is on the carbon dioxide. So this is one that kind of leads me to think that they might be overventilating a bit. I mean, it's always in the good air exchange range, which is fine, but it is borderline outdoor air in terms of the CO2 levels, which means that they are basically at the same level of outdoor air in terms of CO2 for like almost the whole year. And so, you know, I could see them being able to back off the ventilation rate a little bit and, you know, letting the CO2 float a little bit higher and still be in good air exchange range. So that's another piece to think about here. Next piece I've got is looking at the volatile organic compounds. And these are all in the marginal, right on the border between marginal and acceptable range. So again, related back to, you know, regular ventilation. They're well within the regular area where volatile organic compounds should be and are not dangerous. So all good stuff in indoor air quality. Next, we will take a look at domestic hot water. So here we've got 2 electric tank water heaters that I have monitored data on. Tank 1 serves 4 units and tank 2 serves 3 units. And in general, they used quite a bit less hot water than we expected them to, with our assumption of 6.6 gallons per person per day at 140 degrees Fahrenheit. So again, this could be a combination of not using as much hot water and potentially just lower occupancy. I'm not necessarily sure on which of those that is in this case, but it is lower than. And I know oftentimes we look at domestic hot water as an area where is that base assumption of that 6.6 gallons per person per day, is that just incredibly low? In this case, it doesn't really appear to be like that. So we will have to, you know, it's just up for debate and some data to kind of go along with it. Another thing to keep in mind here, right? This is senior living. It's not like there are small children or like families or anything like that, which would probably use a lot more domestic hot water. Okay, now we're going to take a look at energy sleuthing and talk briefly about heating and cooling variables, because the next couple of things are kind of interesting in regards to the ventilation system and the heating and cooling. So all the variables I know of and kind of looked at in this scenario was actual weather conditions, what are the indoor set points, what's the ventilation rate, is there a potential for opening windows at inopportune times potentially, and then just in general, the system efficiency. So first thing we'll take a look at is, so the way this works is it's outdoor condenser, it's ductless split heat pumps, and this outdoor condenser serves refrigerant lines to 8 individual heads inside the building. So each apartment basically has a head, the hallway's got a head, all that kind of stuff. And this is the distribution I had to deal with in terms of these 2 heat pumps that I had data for. So heat pump 1 is in the light blue on the right-hand side of the screen. So that served all of that first floor level, as well as some spaces on the second floor, which will be on the next slide. And then DSHP2 served that middle corridor along with those south-facing kind of units, as well as more spaces on the second floor. So this is the second level. So DSHP2 then serves, you know, all of these units on the second level, which have more exposure to the roof above, and DSHP1 serves just the units, not the corridor on this level. So all in all, they serve about the same area in terms of square footage of what they're serving and volume of air, but the loading profiles are different, right? DSHP2 has mostly south-facing glazing and quite a bit of, exposed interior spaces on the other hallway areas. And DSHP1 is entirely east-facing windows for the most part. There's a little bit of north-facing, but not a ton. But basically, the energy difference here was really kind of startling to me when I took a look at the next slide here, which is showing the monitored heating and cooling over the course of the year. DSHP1 is in the gray, so it is fluctuating pretty greatly in comparison to DSHP2. And I'm going to go into more detail on this because our predicted energy use, just during pre-certification was about the same profile, but a factor of about half. It was a lot lower in terms of what we predicted the heating and cooling was going to be. And my next slides are going into energy sleuthing and trying to figure out why is that dashed line so low? What are variables we could look at that would, in real life be different than what we did in our energy model? So the first and foremost is weather. What was the actual weather during this time? And what did it do to the building? One thing I do want to bring up with this weather data is that I don't have solar radiation data. So I don't really know, and I can't change what the sun did in the energy model, but I can look and change what the average monthly temperatures were, from real life compared to what was in the energy model. So this slide with the now a solid black line is showing basically how the weather affected our original modeled climate, which is the dashed line. So it didn't change a ton. In the heating season in 2019, it was slightly colder than what the climate data was estimating it would be. And in the 2020 season, over the course of the heating season, it was a little bit warmer. And cooling season, again, it was slightly warmer in both 2019 and 2020. But marginally so, right? This didn't really impact the annual heating or cooling. It really just changed where the loads happened. So this was just interesting to see, it kind of explains why, okay, it's colder in December of this year than it was in January, while the modeled data thought January would be the coldest month if you're looking right in the middle here at 2020, right? So this was the modeled climate peak. But the actual climate peak was somewhere. Next variable, and this is the biggest one for sure, at least in this first section here. The indoor set points are really critical, right? Like that plays a big impact, especially when you're trying to look as granularly as we are at heating and cooling data. So this is what our energy model thinks the set points are, right? We think it goes between 68 in winter and up to 77 in the summer, and then back down to 68 the next winter. So it's pretty rigid, and I know it's probably, it's pretty wide, right? Like it's a big range. But the actual monitored data we got was like even more surprising than I thought it was going to be. I mean, I know it's senior living, but this whole array, right? They're keeping it colder in summer down at 74, and they're keeping it up at 78, 79, almost 80 in the winter. And kind of going into March, right? Like up in here, this is hitting 80 and they're mid-February. So, set points wise, it kind of fluctuates a lot, in this hallway temperature in unit 104. So this is just interesting to me to see, like they are definitely kind of almost the opposite curve of what we were expecting, right? We were expecting them to let it float a little bit lower in the winter and float a little bit higher in the summer. And honestly, they're doing basically the inverse of that, which is pretty interesting. And the impact here is that on an annual average basis, they were keeping it about 77 degrees Fahrenheit in the heating season across 2019 and 2020. And in the cooling season, they were keeping it lower at about 75. So that green line now represents, okay, I've updated the weather data, and now I've updated what the set points are. And that's a pretty big jump, right? We got about halfway to what the actual monitored data was. So there's definitely tons of discussion we can have about, set points versus energy modeling, and it's all going to be fun to get into after the presentation. So next one I will talk about, and I have here basically on out is more questions than answers, unfortunately, but ventilation wise, this system was commissioned and measured on site on October 4th, I think, somewhere around there. And for some reason, I've got data where it kind of ramps up over the course of about 4 hours, about 10 days later or 6 days later. And it's about 60% higher measured ERV data. And I don't really know why this could happen. I mean, these are small EV 90p units. They don't really have the function to ramp up or ramp down. It's kind of on or off with those types of units, and then just balancing them with the with dampers and stuff. So it could be that airflow is restricted somehow, or maybe somebody plugged another device in. I don't even know if that's possible. But there's something weird that happened on this day over the course of 4 hours that made the wattage of these ERVs increase by about 60%. And then jumping forward, right, because this is almost 2.5 years ago at this point. Now, when I looked at this data in April of this year, it's still about 25% higher. It did kind of ramp back down from that original big jump. But I still don't really know why it's still about 25% higher than what was measured originally. Could be, the filters might need to be cleaned. Could be anything along those kind of ways. But it's just interesting for this first set of ERVs. The second set, which is just 2 ERVs, I think, is an even more drastic increase on the same exact day in almost the same time frame of about 4 hours. It jumped from about 210 wattage measured to up to 670. And again, I do not know why this happened, and it's just it's a mystery at this point to me. It's got to be something to do with airflow restriction. But the fact that it happened over the same 4 hours on the exact same day as the other 3 units, I'm just not sure why this would have happened. But it, again, has kind of evened out and dropped a little bit. It's not at 670 anymore. It's about 540 watts, but it's still, a factor of 2.5 higher than what the rater originally measured. So, oh man. Oh, good. Mike is on here. Good. Mike Duclos is here. He'll have plenty of information to give on this project too. So basically I ran a brief experiment of, okay, what if they did actually increase airflow or something like that, and the fan wattage went up a little bit for some reason. And that yellow line here, which is above the green, just doesn't, it's not satisfying, right? It doesn't really do that much to the whole model. So I don't think this is a reasonable thing that would have happened, and I don't think it's going to perform worse or anything like that. I'm just not sure at this point. And I'm just, looking at all of the different aspects that could potentially impact this heating and cooling stuff. So that's what I've got on ventilation. It's kind of interesting. Next one is operable windows. And this one was just kind of a suggestion, right? Like these are people potentially set in their ways, right? They could have set the indoor set points the exact same as they did in their old homes. Maybe they have the same mindset for opening windows. When you get warm in the winter or something like that, maybe they open them at a very inopportune time, right? So the best way I can model that is to take a look and come up with a scenario. What if 13 windows, basically 1 window per unit, is open about 6 inches for 3 days a week, a whole year round, regardless of if it's nice out, regardless if it's not nice out, which results in about a 0.1 ACH at natural pressure, about on average. So if we're looking at window openings in the winter, you can see that's a much bigger impact, right, than even looking at adjusting the ERV. It's almost on the same scale as, when we just change the set points. So this is a potential thing that could happen. You could just have people who open their windows when they get warm instead of changing the set point, or they forgot to close their window or something along those lines. But just an interesting thing to take a look at. And then the last thing we'll talk about briefly is system efficiency. And I've got minute data here, basically, for the heat pumps. And it's pretty interesting to look at when you start to really dive into the specifics of it. So there are a couple of things in here that are, stuff that we just don't necessarily know at this point. I think an on-site investigation is going to be potentially worth it, especially for this heat pump 1. And the reason I say that is because this is looking at just one day in December of 2019 of looking at what did these 2 different heat pumps do. So heat pump 1 is in blue, heat pump 2 is in orange, and it really, cycles a lot in heat pump 1, and especially in comparison to heat pump 2. So the next thing I wanted to take a look at was to basically now zoom in and look at like 1 hour. So looking at an hour at like 9 in the morning and looking in more granularly. And I don't know if this is necessarily, a big enough time step to do this. I would almost like second data in these scenarios. But basically the heat pump 1 cycled on and off every 15 minutes in that 1 hour. And then that gets multiplied out by the whole day. So I don't necessarily know if this is a main reason why the heat pumps is using so much more energy than normal. I've kind of got some assumptions here and some guesses as to what could be going on, but it's really interesting to see, that it spike and drop down, and you see this happen much more gradually, right, with the DSHP2. It is doing the same thing, right? It spikes, it's just over a much longer time period and then drops down and then spikes. So it could be a couple of things that are happening here that I don't necessarily know. But this did happen on quite a few days where it wasn't even necessarily that cold out. Like on this particular day, I think the average temperature was only about 40 degrees. So I don't even know if it was, I don't think it was defrost. It could have been, or running on a different cycle or something. But basically at this point, it could be that, they do have ductless heat pump heads in each of these 580 square foot apartments. And maybe that half-ton head is simply too big. So maybe that's why it's short cycling a little bit. It could be equipment malfunction. We could have undercharged unit. There could be a leak in the refrigerant line. There could be some kind of glitching going on that's causing backup resistance rather than running on the compressor. Basically, I don't know. I've never been on the site, but I do think we should have some kind of on-site look at this and basically see, is there a reason, any particular reason heat pump 1 is using so much more than heat pump 2, even though they're serving about the same area. So any way you look at it, I took a look at, okay, what if we derate, the manufacturer rated efficiency of the heat pumps for both the heating and the cooling? And I did a 10% duration. And what does that give you? And basically it gets us all the way to the actual measured energy use, pretty close with that red line there. So this is something that's interesting in terms of, all of the different variables that go into this energy modeling versus actual monitored stuff. And, if this wasn't monitored at all, no one would have any idea. I mean, according to a couple emails I've had with I think the developer over the past couple of days, from a financial standpoint, this building is performing really well, right? Like they're perfectly happy with it. There haven't been many issues at all. So it is doing well. It's just me and the rest of us looking at this as energy nerds and looking really, really closely at data that we are, specifically looking at the heating and cooling so closely that we really want to just have answers. And it annoys me personally, that why is the modeled data so much lower than the measured, right? And looking at all these variables kind of helps me get a little bit more closure. And okay, we can't predict everything. At some point, you just have to do your best. So with that, that's about it for me. Yeah, that's it. So questions, I'm sure there are tons.
James, thank you so much. That was great. Yeah, so we'll open it up and Sean will concierge some questions. And I'm going to toss one in there too.
Actually, Shannon is our guest concierge today. Yes.
Awesome.
Yeah.
That's okay. I can do an impersonation of Sean, I think. Hey, everybody. Happy to be in for Sean tonight. And we have first questions coming up from Christine. Christine, would you like to unmute yourself?
I was just curious about, you mentioned that some of the units, the ERVs, I think it was 2 ERVs were measured, but there were 5 total. And then the heat pumps, same thing. And I was just curious why they were not all monitored.
Great question. So the whole monitoring for this project was funded through FIAS's Industry Advisory Council. And basically we had funds to measure 2 units, like 2 individual units. And it just so happened that this project, ideally we would have had individual heat pumps assigned to that unit and just had a one-to-one measuring. But this was such a weird distribution of decentralized systems that they had to measure all 8 of the indoor heads with that outdoor compressor. And then we just have to figure out which one is the energy use of our one unit. And that's kind of how it worked out with the water heater, the ERV, and the heat pumps. That's why it was a weird web to untangle. Ideally, it would have been all one-to-one, right? One heater for that unit, one ventilation unit for that unit, all that kind of stuff.
Gotcha. Thank you.
Yeah, thanks for your question.
Thanks, Christine. Next, we're over to Barbara in OZ.
Hi, thanks. I just wondered, because I'm looking to design a kitchen for my new house, this whole recycling versus extraction of air. And I know you said that you've got a hood that's recycling. Do you have any experience with extraction or with the kinds of stoves that recycle the air through the stove rather than through a hood, pull the steam straight into the stove, into the filters?
Yeah, good question. Most FIAS projects, most passive projects use recirculation range hoods in my experience, and that's mostly just to retain the heat. They don't want to just take all that heat out that you spent so much energy to keep conditioned. I do know that the exhaust range hoods typically provide, well, if they're designed properly and actually cover the stove and are used, they should technically provide better air quality, right? Because they're going to get all of the smoking fumes out of the building, directly out, rather than relying on filters. But to me, the question is, how many people use them? If it's really loud, it's probably not going to get used. Sometimes they're installed ineffectively, right? They're too high above the cooktop, or they're not deep enough. All of these things are considerations, but going forward, FIAS is aligning with IAP, which is Indoor Air Plus version 2.0, which I believe is going to require direct exhaust range hoods for single family homes. This is not going.
Is that a new regulation? I missed what you said there.
It's Indoor Air Plus is a prerequisite program that FIAS relies on to help with indoor air quality. So it's not a code or anything like that. It's basically a regulatory group. And this will only affect single family homes. It's not going to affect townhomes or multifamily projects. Those are still going to be allowed to use recirculation range hoods. But in general, we're gonna start requiring exhaust range hoods for single family projects, just because that's what Indoor Air Plus does. And there's a lot of data out there about, especially in marrying exhaust range hoods with a gas stove or something like that. There's a huge difference between gas-fired stoves versus an induction stove or something like that, where you're also trying to make sure there's no, excess gas particles in the air and stuff like that. So, yeah, good question though. I don't have very much experience with the third type you mentioned. So unfortunately, I can't speak much to that one.
Yeah, it may be somewhat new. Great, thanks very much.
Thank you, Barbara. I'm going to jump the line just for a second because it's a related question from Tom Phillips that just came in, if Tom is ready.
Yeah, if I can remember what, I think it was basically about the range hood stuff. It was one of them, I think you answered it. Ideally, you could have measured particles, because some other studies have found that the recirc hoods don't work very well for particles and a lot of other things. So, most IAQ people do not recommend those. And California may have already required those in previous building standards to be ducted exhaust range hoods, not recirc. And the new upcoming standards will probably have a differential between gas and electric stoves that require more ventilation rates, higher ventilation rates for gas. So anyway, thanks. Great talk.
Yeah, that all tracks for me. Thanks, Tom. And I think Mike Duclos, come on, man. I think you're up next.
Yes, hi, James. How are you doing?
I'm doing good, Mike. How are you?
Good, thanks. So there was a design cost trade-off here. Originally, I had pushed for cooktop exhaust outside. And when the cost of that became known by running the numbers, there was a lot of incentive to try to go to recirculation, which, as we all realize, is not going to provide as good indoor air quality. So what happened is this: in order to get Energy Star certification, we had to go and discuss this with, I forget the gentleman's name at Energy Star, and he required we pull 25 out of the kitchen and of course 20 out of the bathroom. So now we have 45 in a tiny apartment. And guess what? The air has very, very low humidity. And we can see that in the CO2 numbers also, right? Very nice CO2, but maybe too nice. As an artifact of this, I talked to James Peterson after he'd done a presentation, telling him about this problem. And he said, yeah, you could use something like a ultrasonic humidifier, right? And give everybody a humidifier and let them run the humidifier. Interestingly, I had someone else who happened to be an industrial hygienist with the same problem, a near passive house building with a wood stove with dry air. And so he put the ultrasonic humidifier in his house and found well into the more than 100 ppm per micrograms per cubic centimeter of particulates in the air. And so being an industrial hygienist, he chased this down and he found out that his well water has minerals in it. And these were becoming airborne. And so I don't know if he started using distilled water or what, but it was an interesting chain of events. And I have no idea what's going on with the power there. For the EV90P ERV from Renew Air, if you throttle the airflow, the power consumption goes down. I've done this with a kilowatt plugged in, closing the orifices, and it moves less air, it does less work, the power goes down. It's a PSC motor, but that's a fact. I have no idea where that power increase is coming from because all of the outlet boxes that those were plugged into are above the ceiling panel. So it's not like somebody plugged something in casually, Anyway, I just want to offer those comments and offer to answer any questions.
Thanks. For those who don't know, Mike, Mike was, very integral in this project too and helped us install a lot of the monitored systems. And were you the rater too? Sorry, the verifier as well, Mike?
I was not.
You were not. Do you remember who was? It's okay. I can look it up.
It'll come to me in a minute. Yeah, I'll put it in the chat.
Thanks, Mike.
Thank you so much, Mike. That was an incredibly great and comprehensive question. And now I have more for you, but I'm going to wait because we have Muhammad Razuli up next. Muhammad, would you like to unmute?
Yes, thank you for the opportunity and presentation, James. I had a question about, so in the context of passive house, everything is kind of measured per square meter. If any of the data was available in terms of the 15 or 60 kilowatt hours per square meter, whether we had that conversion. And my second question was whether any of these measured data on passive house projects, whether there was a mechanism to feed this back into the PHPP kind of in terms of modeling guidelines with also future weather files to account for maybe higher cooling loads and also warmer weather in new PHPP. So kind of a two-part question. Thank you.
Yeah, thanks for your question, Mohammed. So to answer the first one, oh boy, what was the first one again? I know the answer to the second one.
Yeah, no, whether you had the data.
In metric.
Per square meter, yeah.
Yeah, good question. I do not right now. Like I could get it, it would just be a conversion thing. But being based in Chicago and this project in New Hampshire, all of the data we were dealing with was in square footage and kilowatt hours and kBTUs. So I don't have it right now, but I could get that pretty readily. To answer your second question, so this is a distinction here, I guess, a little bit, and maybe splitting hairs. But so FIAS is based in the U.S. and we're not really affiliated with the PHI, so we don't use the PHPP anymore. We use a program called WUFI Passive. So that program, and I don't think the PHPP does this either, but neither of them is really suited to plug back data back in. You could do it manually, like I kind of did, to kind of try and plug back in and figure out, okay, I know they used less plug loads, so I lowered the plug loads a little bit. I know they used more cooking, so I raised the cooking a little bit. You can do it on a manual basis, but I don't really think either of them is really set up to, you know, just take a plug-in of like, okay, I've got this hooked up to my SiteSage docket and it'll just like download to me for the program. Nothing's really set up like that yet. I'm hoping in the future we could have that. That would make my job basically obsolete, which would be super nice. But the other part too, you know, talking about data and stuff like that, I had to do that manually as well, basically input the data, you know, override the existing climate data file and put in what the actual temperatures were. And you could do that any way you want, right? We did investigate and looked at future climate data using media norm to kind of predict what 2050 would look like, 2070, stuff like that. And to me right now, that weather data doesn't really look correct to me, you know, based on what we've been seeing. Most of the changes we saw were in the annual demands and for cooling and heating that it changed, but it didn't change the peaks, which based on last week, you know, Portland and stuff like that, doesn't make any sense to me at all. So I feel like the programs that kind of generate future climate data aren't really there yet. Like I don't think they exist at a super decent level for us to use and kind of make executive decisions on. My best solution, I think, going forward with thinking about future climate data and stuff like that is to give occupants options in terms of cooling, especially, you know, give them as many passive options as you can and try and size the systems properly so that it can handle, you know, 112 degrees when that's never happened before, stuff like that. From an energy modeling point of view, though, the data I don't think is there yet in terms of future data.
Thank you, James.
Yeah, thanks for your question, Mohammed.
Thanks, Mohammed. And now over to Zach.
Thank you. Yeah, so everything we do with the Passive House Accelerator comes thanks to our sponsors. So a big thank you to our founding sponsors, 475 High Performance Building Supply, Baxtingui Architects, Mitsubishi Electric Train HVAC US, Partel, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification Units, RDH Building Science, Rockwool North America, Stocorp, and Zola Windows. Our champion sponsor is SIGA, and our stakeholder partner is NYSERDA, the New York State Energy and Research Development Authority. Also, thank you to our patron sponsors, AeroBarrier, BR+A Consulting Engineers, Brennan Air Tightness and Insulation, Inotech Windows and Doors, and US Engineered Wood, TSET. So big thank you to our sponsors. So a couple of announcements. Tomorrow at 10 a.m. Pacific, 1 p.m. Eastern, we have Sam McAfee from Zola Windows joining us for a Passive House Component Spotlight looking at window and door solutions for landmark restorations. So he'll be diving into simulated double hung windows to door solutions, front entry door solutions for landmark buildings, as well as big glass and inside outside connections on the rear side of buildings. So it should be a great kind of triptych of information around windows. So please join us, and I'll share a link right now to register. And then next week for Construction Tech Tuesday, we have Josie Constantini of Schiltes Construction coming to present about Passive House window installation details. You may recognize Josie from her appearance at the She Who Constructs Summit a couple of months ago. We're really looking forward to seeing her on Tuesday. And then next Wednesday, we have Satpal Kaur coming to talk about the hidden story of building injustice and looking at how that impacts the high performance building space and ways to remedy it. So very interesting happy hour presentation coming up next Wednesday. Finally, please mark your calendars for the 2021 New Gravity Conference, the Accelerated Edition, which is a collaboration between Green Building United and Passive House Accelerator. You may know the New Gravity Conference has a rich history for the last several years, bringing together high performance building and affordable housing. And we're going to do that in a fast, fun, and factual way on the 21st and 22nd. I will include, yeah, there is a party at my house, sorry. We have 3 10-year-old boys living it up next door. So with that, I think I'm done. Thanks.